Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside. Let's do some math. Let's review Chapter 8 in the Big Ideas Math Integrated Math 2 textbook on similarity. Everything from dilations to similar figures to similar triangles to triangle proportionality or proportionality within a single triangle itself. What I call the side splitter theorem or what have you. Let's do it. 6 sections of stuff. If you want to download this PDF, it's 3 pages worth. And you can also check out graph paper that I'm going to have for you, assuming we do graphs because of the dilations. And it only showed 17 problems, but they do some examples before that I like to point to. And the examples don't always have to do with the problems you have. They just kind of cover more of the stuff. Not everything is covered in full. And if you want to find more review stuff on this Chapter 8 material, the next video that should be coming out for me is the Chapter 8 test and cumulative assessment, also from the same textbook. And then I'm also going to have a packet titled, Are You Ready? Which is material made by a colleague of mine, which is just more review for stuff for my own personal students when it comes to them and their tests. So you're going to get a lot of different material here. Now, I say this and then I don't know if I always follow up on it, but you know, this is the kind of thing where I've spent hours doing other problems of these types and I've taught them and I've gone over the lectures and stuff. So if there's something that I ever do quickly, it's because it's under the assumption that you've learned it at some point, even if you're taking a class with it. Yes, this is the review for everything, but this isn't your first time hearing it, or it's not supposed to be. Now, you may be revisiting 8.1 for the first time in a while, but if I want to spend time going over something, I will. If I want to speed through something, I will. So just so you're aware of that. So check out the timestamps down below for the particular problem or section that you're trying to find, and hopefully I have everything laid out for you right there. But without further ado, guys, let's go ahead and get started. We're going to look at section 8.1 on dilations. Here's an example of them graphing trapezoid ABCD with vertices here, plotted in blue, and its image after a dilation with a scale factor of 2. Now here's the final result. And what they do is they take all of their x, y values and they double them. Scale factor of 2 means it'll be an enlargement. They're going to multiply everything by 2. 1, 1 turns to 2, 2, and a goes to a prime right there. And b goes from 1, 3 to 2, 6, b to b prime there. And you can see that they all go in this line expanding from the origin, kind of like that. It's kind of this flashlight effect, if you will. A, B, C, D. I'm not drawing perfect lines, but you can see them coming from the origin because the origin is your center of dilation. So multiplying them by 2, that's what you get. And that's the example that they have. We're going to do some of our very own. So numbers 1 and 2 tie in exactly to that kind of thing. So let's look at number 1, where we're going to We're going to graph a triangle and its image after a dilation with scale factor k. Now, a word that they use, image, is actually a geometric word. It really means the figure after transformation. The figure before transformation is actually known as pre-image. I don't know how often the book mentions it. I believe I remember seeing them say it once. Doesn't mean it's the only time, but yes. What we're about to graph here is the pre-image. And I'll use blue and green generally is what I tend to use on these. So 2, 2 for P, 4, 4 for Q, 2, 2, 2 P, 4, 4, 4 Q, and R is at 8, 2. Now you'll also notice on the one from the example that what they do is they also label the corresponding points. I have a fly in my room. They label the corresponding points with the same letters, but using what's called prime notation. That little apostrophe is what we can call P prime, Q prime, or sorry, A prime, B prime, C prime, D prime. We're going to have a P prime, a Q prime, and an R prime, and things like that. So look at this. They have the scale factor of 1/2, K equals 1/2. Let me adjust this. I'm going to write this stuff above. So let me bring these things downward. You can still see the graph, right? Okay, perfect. So we're going to have P at 2, 2, and I'll make sure to do this for the other problems as well. Q at 4, 4, and R at 8, 2. We have a K value of 1/2. So now we're going to take these values. We're going to multiply them by 1/2, which means divide by 2. We'll have P prime at 1, 1, Q prime at 2, 2, and R prime at 4, 1. This is known as a reduction, and we will graph them, plotting them with those primes. So P prime at 1, 1 will be right here. Hopefully you can see them by the colors because there's another P that's right next to it. Q prime, I put 2, 4. I apologize. Q prime's at 2, 2. Q prime's at 2, 2, which is exactly where P was to begin with. So there's Q prime as we reduce toward the origin, and R prime is at 4, 1. Now, the entire chapter is on similarity. If you're this far into it, hopefully you've picked up on what similarity is. We haven't looked back at dilation since, so maybe you forgot, but these objects are similar. These objects are similar. Now, what we did with dilations, we paid more attention to distance to center of dilation. So P prime is half the distance toward the origin compared to what it was. But really, when you look at compare PR's length of 6 to P prime's R prime's length of 3, you'll notice that the 1/2 also applies in that way. So the objects are similar. Angle measures are preserved, right? Corresponding angles are congruent, which I'm really speaking more on like section 8.3, 8.4, 8.5, and 6. But corresponding angles are congruent. Corresponding sides are proportional. All right, number 2. Let's write these out first. X is at negative 3, 2. Y is at 2, 3. Z is at 1, negative 1. You have a scale factor of negative 3. Scale factors can be negative. We'll check out the effect. Let's go ahead and get what those results are first. X prime, we'll graph it after, but X prime is at positive 9, negative 6. Y prime is at negative 6, negative 9. And Z prime is at, Z prime is at negative 3, positive 3. Multiplying by negative 3. Okay. Now I may have to kind of get something out of range here, something you won't be able to see. So can I say these out loud? Can you take a look at those, write them down and such, and me say them out loud because I got to move down here? Okay, X prime is at negative 3, 2. Excuse me, X. X is at negative 3, 2. Y is at 2, 3. Y is at 2, 3. I'm asking the question, why? How come? X, Y, and Z is at 1, negative 1. Here's the original, pre-image, non-transformed triangle. Very thick line. Let's do that again. And then let's see what happens to X prime, Y prime, and Z prime. X prime is at 9, negative 6. Now, before it was in the second quadrant. Now it's going to be over here. What the heck happened to this thing? It went through the origin and out the other side. Instead of tripling this direction, it's tripling its opposite direction, basically. Y prime is at negative 6, negative 9. Down her. And Z prime is at negative 3, positive 3. So you can see that they do go in opposite directions in a way. In such a way that this actually becomes, and we'll talk about this more for section 8 too, but it becomes a rotation, a 180-degree rotation. Also a dilation, but there are two things that happen with that. Dilation, enlargement, and that rotation. So Z prime goes through the origin to Z, Y goes through the origin to Y prime, X goes through the origin to X prime there. And there's the graph. Okay, let's move forward to number 3. You are using a magnifying glass that shows the image of an object that is 8 times the size of the object's actual size. The image length is 15.2 centimeters. Find the actual length of the object. This actually harkens a little bit more now. I'm sure it had to do in this section, but this reminds me of similar figure stuff now. You're using a magnifying glass that shows the image of an object 8 times the object's actual size. So when you take an object, I don't know, I'm going to make an algebraic equation. We could do a proportion. Hey, you know what? We could do a proportion. Let's do that. The original image, if it was 1, there's a 1 to 8 similarity ratio from the original image to the magnified image. The image length after using the magnifying glass is 15.2 centimeters. We need to find the original actual length of the object here. So there's the 1 to 8. Now when I cross multiply, I get 8x equals 15.2. This is the equation I was going to write, but I think it just makes more sense to see it that way. And divide by 8, you get x equals something. It's not a whole number, but it's it's like a normal number. 1 point. I don't know. I'm gonna do a calculator. I should know. I should know. 1.9. I don't know why that took me a while. I was going to say 1.8 and it wasn't that and I gave up. So 1.9 centimeters for the original object because it needs to be 8 times smaller. We need to reduce it by 8 times basically. But that proportion thing is going to carry through a lot of other problems in a moment. Okay, let's go to section 8.2 on similarity and transformations. More dilations will occur, but other kinds of transformations can occur, and you can see where we're going to be doing graph things, or looking at graphs at the very least and saying what happened to them. Describe a similarity transformation that maps triangle FGH to triangle LMN as shown to the right. Now, before we start on the problem, keep in mind that now these ones do not use prime notation. We are now starting to lean into the concept of similarity where objects can appear in different, where you're going to see two objects and they might not be oriented the same way, but parts will still correspond. And we got to look at the way that they're ordered in letter order for this to work. F is the first letter, L is the first letter. F corresponds with L. G corresponds with M, H corresponds with N. So when we look at F, G, H, and L, M, N, you have to ask what other kind of thing occurred other than dilation. And the answer is a rotation. This thing took this object and it laid it on its side, kind of like, actually they have a drawing down here. They laid it on its side like this, rotating at 90 degrees counterclockwise. So they are probably going to bring that up in some way. Yeah, if you rotate triangle FGH 90 degrees about the origin, and if they don't say the direction, that means it's counterclockwise. Then the image F prime, G prime, H prime, that triangle will have the same orientation as LMN. So look at this 90-degree rotation. I'm not going to get deep into the rules of the rotation. That's more integrated math 1. We'll do a problem with it, maybe. But when you see this here, now look at the red one. It's now oriented the same way, where corresponding points, F with L, G with M, H prime, or primes, H prime with N, they now all correspond in such a way that all we need to do is now dilate. And it looks like by a scale factor of 1/2. So they're going to do both of those. So I said this in 8.2 at the time, and I'm saying it now. There's a lot of intuition. You got to be intuitive for this one to work out. You got to understand your rules of transformations. You got to know how corresponding parts work. So there are two things that happen. Similarity transformation is a 90-degree rotation counterclockwise about the origin, followed by dilation with a scale factor of 1/2. And the 1/2 can come in several forms. You can look at any such points, -2, 2 to -1, 1. You can look at this length go from 4 to 2, because as I said, those things pop up that way. A lot of things you can do. So let's look at our problem set that we have, starting with number 4. We have, let me graph these. A, B, C as a triangle, and then R, S, T as a triangle. So ABC will be at 1, 0, -2, -1, and -1, -2. A, B, C. With this one, although we could count, like, I don't do distances, like distance formula, but you could count like slopes, like, hey, B to C is down 1/1. It's not an actual length. I generally like to do those lengths when there's a horizontal or vertical line. I might be able to use it here if I want to. Excuse me. R prime, not R prime, R is at, and I can already imagine it's some sort of reflection or a rotation. R is at -3, 0. S is at 6, -3. Okay, I think it's a reflection. S is at 6, -3. And T is at 3, -6. And they do mention, I didn't read it, describe a similarity transformation that maps triangle ABC to triangle RST. That means that A corresponds with R, B corresponds with S, and T corresponds with C. And you're going to, whoops, I guess I can't do that. I wanted to move C. You're going to sometimes be able to look at a drawing and say that you can tell which way it's supposed to go, but you can tell that this green triangle is the blue triangle but flipped over. Not rotated, but flipped over. And flipped over the y-axis, right? I could do a dilation, but it's easier to see the dilation after the reflection of sorts. So the first thing I want to do is reflect this thing across the y-axis. Make the y-axis a mirror image like this. Boom, 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 boom. And across that line, A would go to the other side right here to be A prime. B would, let's draw that. A would go to the other side to be A prime. Let's thin it out a little bit like that. B would go 1, 2, 1, 2 over to the other side to become B prime. And C prime is like that. So kind of rough sketch connect this thing, guys. I don't want to make it stand out too much, but I do want you to have to pay attention to it next to the green. A prime, B prime, C prime is this reflected piece across the y-axis. So now it's actually facing the same way as green is in such a way that we can do a comparison. So if I'm going to describe this transformation, I begin by mentioning that you reflect triangle ABC across the y-axis. I believe the book would say in the y-axis, but it means the same thing when all said and done. So reflect Reflect across the y-axis, there's the first thing. Now we need to map A prime to R. It looks like this is about to get tripled from the origin. It's -1, 0. We have -3, 0. This is 2, -1 for B prime. S is 6, -3. You triple those. And C prime is from 1, -2 to now 3, -6. Everything looks like it's getting tripled. By the way, remember how I said the whole down 1 over 1 thing? Well, S to T is down 3 over 3, also tripled. So hopefully this makes sense. Then followed by a dilation with the scale factor. It looks like we're going to have to say from the origin. A scale factor of 3. So we do enlarge. Okay, there's number 4. We still have 2 more to do. So if I over-explained, it's something where I probably will explain less here. However, there's probably a new type of transformation to talk about, either translation or rotation. So we'll check it out and see what we have. Number 5. In number 5, I have A at 6, 4. It's so big we might have to reduce. A at 6, 4, B at -2, 0, and C at -4, 2. Once again, nothing that's horizontal or vertical from these points. I have to sneeze. Excuse me. It's probably super attractive to do on webcam. On camera. Ready to pause my video in this moment. A, B, C is right like that. R, which corresponds with A, is at 2, 3. S is at 0, -1. And T is at 1, -2. Whoops, let me move that S letter out of the way. And T is at 1, -2. Okay, Well, this one's interesting in that, remember, T corresponds with C. This one's interesting in that I don't think that we covered this kind of reflection, because this looks like a reflection to me. It does. You might say, wait a second, if it was reflection, wouldn't it go like this? It's not that kind of reflection. You can reflect across more than just horizontal and vertical lines. When I see this as a reflection, I say that because of the things that correspond. C corresponds with T. C and T are over, let me use a different color. C and T are over on these sides, whereas B and S, which correspond, are here, and A and R correspond there. There's clearly a dilation that goes on as well, but how does C go across this other side to T and B is as close to S here? That's because there's a mirror somewhere in the middle. And when I say mirror in the middle, I'm talking about this line here. And this is one of those things that you either know or you don't. I'm just going to say that right now. Either you know or you don't, and maybe it takes a dilation first to recognize what you have to do. And I probably will do a dilation first. But you guys see this line? This is called the line y equals x. And I'm very expecting that this is what we have to reflect across. How would you know this? How would you know to do this? Part of it is you're convinced that it's a rotation because the way that this thing kind of moves upward now instead. But it can't be a rotation for 2 reasons. Number 1, A would be in a different quadrant than it is now with R. Number 2, B is closer to S and C is farther, or, B and S are closer than C and T are. It's not a rotation in that kind of way. So this is the line we will be reflecting across, and I'm going to keep that in mind for this problem as I back it down and behind the blue and stuff like that. I'll keep it behind it. Now, I'm thinking about doing a dilation first. I guess I won't. I'm going to go ahead and do the reflection. I want you to be convinced as to what I'm showing here. I need to convince myself that that's what this is first. But let's go ahead and try that out. I'm going to plot A prime by reflecting across here. One away in that direction like that. And this would be my A prime. B prime would be one away like that. And C prime would be 1, 2, 3 away, 1, 2, 3 away like that. After a reflection across the line. Oh, by the way, I don't know if I mentioned the line. This is called the line y equals x. This is the line y equals x. Literally, if you think about slope-intercept form, that's what this thing is here. I'm going to move that B prime point label. Oh, can't do it without moving that as well. Okay. Sorry about this. A lot of explanation, a lot of look-sees at what it is we are doing. Probably just easier to rewrite it. Okay. Can you do your best to ignore the blue? Let's just kind of hide that away. Look at purple, look at green. Look at purple, look at green. Let's hope you're not suffering from deuteranopia or something like that. You don't have color blindness and look at these as both as blue. Look at this, A prime, B prime, C prime. Look at R, S, T. They are oriented the same way. Clearly one's bigger than the other. How much bigger? Look at any of the lengths. R is at 2, 3. A prime is at 4, 6. That's double. S to T is down 1 over 1. B prime to C prime is down 2 over 2. That's double. So these are doubled. We have to reduce them to half their size. So it's going to take two things. We did one of them. The very first thing is reflect triangle ABC across the line y equals x. This is not the x-axis. This is not the y-axis. It is a diagonal line. I'll just put the line y equals x. Y equals x, followed by, there's not much room for me to write this, followed by a dilation, how do they say it? With a scale factor of 1/2. So this also has the scale factor of 1/2 there. All right, these problems are taking a little bit longer because of just the way that they're natured. I didn't know if they would, and they are. Number 6. I mean, look, I don't recall doing a problem across the line y equals x during the entirety of section 8.2. Not in an example, not in the problem set, never. So I think it was worth bringing that one up. Number 6, A is at 3, -2. B is at 0, 4. C is at -1, -3. Getting my size ready. There we go. Okay, A, B, C. Let's find the ones that correspond. Let's look at where R, S, and T go. R is at -4, -6. S is at 8, 0. Looks like a rotation because B goes to S here. And T is at -6, 2. Okay. I'll label them in 1 second. RST. Now, none of these were translations, unless this one has some form of translation. I don't believe it does. But can we agree that this one's probably a rotation? That this ABC is taking its form, because A goes with R, right? It's got to somehow go down. B's got to somehow go down. C's got to somehow come up, right? A rotation. And a 90-degree rotation at that. How do we do rotations? A lot of people have trouble with those. Would help if I didn't have R, S, and T in the way. So I don't know how to do this. But I would like to take these points here for A, B, C. I'm going to kind of do a quick grouping, and I'm going to reset this after. But I'm going to take this and rotate it like that, basically. You see that? I'm going to do that. So I'm going to take those points and put them there. So you got to be really good at recognizing those things for what they are. If you have trouble, rotate your own paper and make that happen. So B was at 0, 4. B prime will be at 4, 0, right there, because it's rotated 90 degrees. This is 90 degrees clockwise, by the way. I do have to stress that. A was at 3, -2. A prime is now going to be at this. This is the hard part unless you rotate your paper. -2, -3. I've done rotations forever, so I know exactly where to go. C is at -1, -3. C prime will be at -3, 1. Right here, after a 90-degree rotation. And here is that 90-degree rotation. I got that for you. Here, here, here. We just saw it a second ago. And hopefully you can see that it kind of looks like the green one. But the green one is bigger. How much bigger? This is not foreign to us. Double. It's double the size. We have to enlarge our own thing. So there are two things we're going to have to do. It begins with rotation. Rotate. Rotate triangle ABC. Man, I really need to stretch this out a little bit more. Rotate triangle ABC 90 degrees clockwise about the origin. About the origin is basically going to happen here. Followed by a dilation with a scale factor of 2. So we're doubling, and hopefully you understand the doubling effect, how far from the origin it's going. All right, there is the last one. I don't know, I think it's the last one for 8.2. Yep. Let's go ahead and move forward to 8.3. Probably less on graphs. I'm looking forward to that, actually. A little less on graphs. 8.3 on similar polygons. Before we actually start the problem set, let's look at the example that they give us. In the diagram, EHGF is similar to KLMN. I'm going to restate again that the letter order matters. E corresponds with K, etc. If that wasn't enough, you look at the diagrams. They look oriented the same. You see E and K there, and it keeps going forward. Find the scale factor from EHGF to KLMN. Then list all pairs of congruent angles and write the ratios of the corresponding side lengths in a statement of proportionality. So the first thing they do, by the way, they do go from EHGF to KLMN, which means it is an enlargement. If it's an enlargement, the scale factor is more than 1. You divide these numbers by these numbers to figure out what you have, and they do exactly that. From the diagram, you can see that EH and KL are corresponding sides, so you can find the scale factor with those or with any set. They did 18 divided by 12. You could also do 21 divided by 14, or this, or that. You'll get 3 halves no matter what you do because they're similar objects. Angle E is congruent to angle K, H to L, G to M, and F to N. In any similar figures, corresponding angles are congruent. Corresponding side lengths are not, however. 12 and 18 aren't the same, but they are in proportion with each other. Whatever this divided by this is, and I just mentioned this divided by this is, this divided by that is, they're all 3/2. And that's all they ask you to do for the problem. You're not doing anything else, and it looks like we are going to be doing the same thing on numbers 7 and 8. So let's go ahead and give it a shot. Number 7, we have, I feel like I want to copy and paste it. I feel like I do. We are going to go from figure ABCD, a rectangle, to figure EFGH. Because it's similar, another rectangle. List all pairs of congruent angles and write the ratios of the corresponding side lengths in a statement of proportionality. Keep in mind, every set of angles are congruent, but let's go based off of the order in which they wrote these numbers. 1, 2, 3, 4, 1, 2, 3, 4. So let's begin with, what do they want? Find the scale factor. Let's begin with the scale factor going from ABCD to EFGH. It looks like, and you know, when you correspond parts, A goes with E, A with E is right here. So as we just referred to before, this looks like a rotation. It looks like that the ABCD got turned over 90 degrees counterclockwise like this. So the 12 corresponds with that 9, and the 8 corresponds with the 6, right? These are linked, these are linked. I want to make sure that you understand that. The longer goes with the longer, the shorter goes with the shorter. So as far as scale factor goes, K, we're going to divide, for example, 9 divided by 12, or 6 divided by 8, and you will get 3/4. There's the scale factor. What else? List all pairs of congruent angles. So this is where I'm just going to do the ones that are, because A is congruent to all of them, but let's do the one it corresponds with. Angle A is congruent with angle E. Angle B is congruent with angle F. You know what I'm going by? I'm not even looking at the diagram. I'm looking at this letter order. Angle C, and it's also alphabetical. Angle C is congruent with angle G, and angle D is congruent with angle H. So there are the corresponding angle congruencies. Now let's do the statement of proportionality. EF over AB. I want to do it as the scale factor. EF over AB is the same as FG, letters 2 and 3, over BC, letters 2 and 3. GH, 3 and 4, over CD, 3 and 4. And EH over AD, 1 and 4, 1 and 4. Those are the 4 different segments of these rectangles. They are in that proportionality. They all have a 3/4 reduction. All right, number 8, we have 2 triangles, also not drawn the same direction, also looking like some form of rotation, or maybe a reflection, no rotation. Number 8, I won't redraw it. You can see it there. XYZ, I'll write this though. Triangle XYZ is similar to triangle RPQ. So X corresponds with R, Y with P, Z with Q. As far as scale factor goes, we do go from XYZ to PRQ. It is another reduction. So K equals, let's look at the hypotenuses to not make a mistake on those. By the way, they do show congruent angle markings. That'll definitely help as well. Like at least that one set, but the right angles too. Let's do the hypotenuses of 10 over 25, which reduces to 2/5. It's a reduction by a scale with the scale factor of 2/5, okay? Now let's write our congruent angles. We do have the markings of the ones that are actually congruent. That does help. Angle X, oh, and we have a similarity statement. Angle X is congruent to angle R. Now I'm looking at this for it, but can you also notice that right here? X is congruent to R. Look at the markings. So angle X is congruent to angle R. Angle Y, the non-marked angle, is congruent to angle P. And then the two right angles are congruent. Angle Z with, angle Z with angle Q. Okay, there are our congruent angles, corresponding congruent angles. Let's now go to the corresponding and proportional sides. If I divided, which I did the hypotenuses. If I divide RP by XY, I should get the same thing as PQ over, let's look at the letters, over YZ, which is the same as RQ over XZ. Honestly, for a review, I'm not going to say those are wasted questions, but I feel like those are built to do what it is you have to do mathematically later. Scale factor, fine question, but those aren't the questions I would be going with on those. Numbers 9 and 10, we have things that have to do with perimeters, areas. Actually, 9 is not perimeters or areas. Number 10 is. Number 9, two similar triangles have a scale factor of 3 to 5. And they're talking about side length things. So I'll kind of make up two triangles here. Boom. And then boom, 3 to 5, they're similar. Okay. The altitude of the larger triangle is 24 inches. What is the altitude of the smaller triangle? Now, when they say the altitude, I assume they mean a corresponding altitude, because that's the idea, right? Altitudes correspond to each other in such a way. I'll call this unknown altitude A, and I'll call this one what it is, 24 inches. Now, we have a 3 to 5 scale factor here, which means if this length was 3, this length would be 5. We don't know what the lengths are, but that's the idea. When you reduce the fraction, this is what you end up with. So we have a 3 to 5 similarity ratio from one to the other, small to big. The small unknown length of this altitude is A, and the larger one that we know is 24 inches. As we cross multiply here, we get 5A equals 72. Divide both sides by 5. You get A equals 14.5. I believe that is 14.5 inches. And I mean, look, that would be the answer. So because the triangles are similar, because we know the similarity ratio, and because altitudes correspond with each other, you can build a proportion comparing one to the other like we just did there and solve. Simple cross multiplication. The problem is I don't know if that's the answer. Not 14.5, 14.4. 14.4. Let me use a calculator. Give me 1 second. 72 divided by 5. 14.4. Okay. Something went wrong in my head when I realized 3/5 is 0.6, and 0.6 times 24 can't end in a 5. Okay, guys, we're going to do number 10. Here we go. Two similar triangles have a pair of corresponding side lengths of 12 meters and 8 meters. The larger triangle has a perimeter of 48 meters and an area of 180 square meters. Find the perimeter and area of the smaller triangle. So let's draw a larger triangle, smaller triangle, and we have a 12-meter set and an 8-meter set. The perimeter and the area of this larger triangle, perimeter of, I'll put like a capital L. I think a cursive L might get a little confusing looking. Perimeter of the larger is 48 meters. The area of the larger is 180 square meters, like so. We don't know the perimeter of the smaller. That's an S. Looks like the Photoshop symbol. And the area of the smaller is also unknown. Okay. What we're going to do is, who cares what the triangle looks like or how many sides even there are, or what the formula for area of a triangle is? None of that matters. The only thing that matters is the scale factor and the fact that we're trying to find perimeter and area. And yes, perimeter's adding all the sides. We don't need the sides. Area is 1/2 base times side. We don't need it. We need the scale factor to begin with. Let's start with that. Assuming we're talking about the reduction, let's do 8 over 12, which is 2/3. Okay, we got a scale factor of 2/3 going from large to small. Now, what you might have learned is that the ratio, and I dub this R sub P, what you might have learned is the ratio of perimeters is the same as your scale factor of whatever you do. So it's also 2/3. Now we can take that 2/3 and set up a proportion that 2:3 from small to big, just as this perimeter of this unknown smaller one is to the 48 meters that the larger one is, like that. Now I can cross multiply and get 96 equals 3 times the perimeter of the smaller, and divide by 3, and you get the perimeter of the smaller as 32 meters. I did not use a perimeter formula. I used the ratio of perimeters being the fact that it's the same as the similarity ratio because it's just an addition of sides. It's still 2/3 the sides of 48, and that's what you get. Ratio of areas, though, you would be forgiven, however mistaken, if you believed that the ratio of areas was the same as the scale factor and ratio of perimeters. No, you take the scale factor and you square it. So 2/3 squared, square the 2, square the 3, you get 4/9. The area of the smaller triangle is not 2/3 the area of the bigger. It is 4/9 the area of the bigger, which is a smaller number. 4/9 is around 44%, 2/3 is around 66%, so it's a small number. So let's take that guy, let's set up a proportion with that involved. 4:9, smaller to big triangle, as this unknown area of the smaller is to 180 square meters of the larger. If I cross multiply that one, I get 720. I don't need to write the square meters right now. 720 equals 9 times a sub s, and that a sub s is going to be 80 square meters. 80 is 4/9 or 44.4%, the size of 180 square meters, and that is the area of the smaller triangle. Okay, let's go and move forward. Let's look at new section 8.4, proving triangle similarity by angle. Determine whether the triangles are similar. If they are, write a similarity statement, explain your reasoning. So the angle similarity thing is basically this. If you know that 2 sets of corresponding angles are congruent in 2 triangles, then the triangles are similar. That's it. Section 8.5 will have side, 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 and side, angle, side. We'll get to those, but angle is this. So in the example, right angles are congruent, C and F. We're good there. 61 is not congruent to 29. No. But if you do your angle addition stuff for interior angle sum of a triangle, 180 degrees, you'll find that the measure of angle E is also 29 degrees. This is what they wrote. Measure of angle E is 29 degrees, 190 plus 61 plus 180, or plus that is 180. So E should correspond with A. They're both 29 degrees. They're also congruent. A is congruent with E, B is congruent with F. 2 sets of angles are congruent in these 2 triangles, so the 2 triangles are similar. They wrote a similarity statement. Triangle DFE is similar to triangle CBA by the angle similarity theorem. Our numbers 11 and 12 were asked to do the same thing. Now, different kinds of drawings. Actually, 12 is kind of closer, but number 11 is not. And let's copy and paste the drawing. So number 11, I have triangle, QRS, and then this TUS. I believe that's the ways that they correspond whenever you see a question like this. I have angle Q. I have measure of angle Q at 35 degrees equal to the measure of angle T. Therefore, angle Q is congruent to angle T. That's one set of congruent angles. You can call that the definition of congruence, if you will, that when their measures are equal, their angles are congruent. You also have a set of vertical angles right here in these S angles, if I call them that. That is angle RQ or RSQ, which is congruent to angle UST because they are vertical angles. The vertical angle theorem, 2 angles opposite each other when lines intersect are always congruent. So I have that set and that set, so I can now make these 2 triangles similar. They do say write a similarity statement. You can come up with your own. I'll do QRS. QRS, you start from the 35 degree one, the unmarked one, and the congruent guy here, to the 35, the unmarked, and the congruent, TUS. Don't put TUV. That is by angle. They say show that they're similar. This isn't determine whether they are. They will be. They're just saying show it. Whereas the example said determine. It's weird that there's a discrepancy between the 2. Number 12. Apparently these are similar as well. Now, these are right triangles, It's going to be a lot like the example one. I guess I'll copy it. I guess. All right. They look like the parts that need to correspond do. Let's see how this works out. We have angle C congruent to angle F because all right angles are congruent to each other. That's known as the right angles theorem. I don't know if we have to write this stuff, but I'm definitely not writing a paragraph proof, so I'm just going to give little reasonings in parentheses. And this part I'm going to do some algebra on. I want to find the measure of angle B. Why not? Because 60 and 30 are not the same. But is this one 30? Oh, it's actually going to be, yeah. The non-right angles in a right triangle are complementary to each other. So this B plus this 60 is going to equal 90. Don't worry about adding the extra 90 to get 180 if you think it's going to be extra work. Subtract 60 from both sides, measure of angle B equals 30 degrees, which is the same as measure of angle E, which means the measure of angle B equals, I just wrote that, which means angle B is congruent to angle E by, again, definition of congruence, if you will, because they have equal measure. So, therefore, triangle, I'll call it ACB, is not congruent. Oh, I put congruent here. I am so sorry. These are not congruent. I just did too many congruent signs. Similar. If I said congruent as well, I do apologize. I'm in a different mindset there. Is similar to triangle, I did ACB, DFE by the angle-angle similarity theorem. Okay. Number 13. A cellular telephone tower casts a shadow that is 72 feet long. Ooh, I gotta draw this. Yeah, this is definitely one of those when in doubt, draw it out kinds of problems. A cellular telephone tower right here, can't you tell, casts a shadow. Here's the ground. The ground will be the shadow. Casts a shadow that's 72 feet long. While a nearby tree that is 27 feet tall casts a shadow that is 6 feet long. How tall is the tower? Let me shrink this tower. All right. There's the tower, and here's the nearby tree. Okay, here's the way that these problems work. Tower and tree. All right, here's the way these problems work. Ground is horizontal. Anything that goes upright is vertical. These make right angles. Right angles are congruent to each other. That's important. A shadow is nothing more than the blockage of light from yourself, but the tip of the object down to the ground is the end of the shadow, which to us, we can see a sun ray go like that and like that. Because these are two objects that are near each other on this planet. I probably should do a line tool for this. But because these two objects are near each other on the planet, they are based, because they say a nearby tree, they're trying to tell you that it's the same sun ray that's being created. Therefore, these two angles are congruent to each other. So these two triangles must be similar by angle-angle. And if they're similar, then we can work out proportionalities to find certain things that we need to. So what do they tell us? The cellular tower casts a shadow 72 feet long. Nearby tree is 27 feet tall. 27 feet tall. And casts a shadow that's 6 feet long. Clearly not drawn to scale. Just go by the numbers. How tall is the tower? So we build off a similarity. I need to find out what this x is right here, basically. So we set up a proportion that I could do like 72 over 6. 72 over 6 equals x over 27. You know, something like that, right? As long as things work out in that way. Now, I could do the cross multiply, all that kind of stuff. I mean, x is on top. What's more important is that we get into the 72 divided by 6 is 12. So 12 is x over 27. Look, if I multiply both sides by 27, I'm going to solve. So 12 times 27. It's a pretty tall pole. 12 times 27, I don't know. I'm not going to goof around on this problem. 324. 324 feet. And note that in a lot of the most recent problems, like number 10 and number 9, we had units. Don't leave out your units for these. Okay, 2 more sections. 8.5 is a lot like 8.4, because it's triangle similarity, but it's not using angle, angle, it's side, 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 and side, angle, side. What are they all about? Well, let me tell you what side, side, side's all about after a quick water break. Okay. Side, side, side in this example is if you have all three sets of sides in proportion with each other, then the triangles are similar. That's enough information to be able to do that, just like angle, angle, and stuff. So you do compare side lengths. 14 is the shortest side here, 6 is the shortest side here. That means you know that your proportionality test will be with those two. So 14 over 6 is 7/3. What's the mid side? 28 here, 12 here. 28 over 12 is 7/3. They call them the remaining because they do the longest sides as well. 35 and 15, 35 by 15 is 7/3. All of these share the same similarity ratio of 7/3. So they're in proportion to each other, all three sets of sides. So these two triangles are similar by side, side, side. Okay, let's do that for 14 and 15 using a certain theorem. Now that was side, side, side. There's also one that's side, angle, side, which actually looks like what we're going to do in number 14. See, I don't know these side lengths B, D, and AE. I don't really have a way of coming up with them. What I do know, however, and I don't know if you're aware of this, let's copy and paste this diagram. What you do know off this, however, is that, and I have to really be careful about what section we're in. We are not in 8.6 yet, so I'm not going to use the side splitter theorem thing, although you could. But what I do know is that this angle C exists in both triangles. It exists in this triangle here, and it exists in the bigger triangle here, the two triangles that we are deeming to be similar. We are going to show that they're similar, but the fact that angle C is congruent to itself by the reflexive property, shared angle in both triangles, tells us that this triangle should be similar to this triangle using side, angle, side. The angle has to be congruent for both triangles, and it needs to be in between the two sets of sides that we know are proportional. We've got to test for that proportionality. So I got to see if 4 over 4 over, let me do this first. I'm going to draw the two triangles separately, CBD. I should have done this first when talking about reflexive property. So CBD and CAE, and these are the ones that are congruent here, but these are the side lengths, 4 and 3.5. This isn't just 8. This is 4 plus 8. This is 12. 3.5 plus 7 is 10.5. These are the ones for which, until you actually know 8.6, and you probably do if you're in the review, but until you know 8.6, we shouldn't be doing the 4 over 8 is 3.5 over 7 triangle proportionality theorem yet. Let's do it the way that they're supposed to be based on the triangles. Let's test if 4 over 12, this is the way I write it, is it the same as 3.5 over 10.5? Well, if you do reduce these fractions, you're going to see divided by 4, you get 1/3. Divided by 3.5, you get 1/3. They are the same. They're in proportion with each other with that. Therefore, and with this congruent angles, therefore triangle BCD is similar, I was about to say congruent, is similar to triangle ACE by the side, angle, side similarity theorem. That's number 14. Number 15. Number 15, you can, CAN, you can use side, angle, side again if you wanted to. You could say angle Q is, congruent to itself by the reflexive property, but this time we actually have all three sets of sides. I got 9, 10, and 14 in this triangle, and then 9 plus 4.5, 13.5, 7 plus 14, 21, and 15 in the third triangle, in the second triangle, I should say. But all three sets of sides. So we can use either side to side or side angle side. You're not stopped with either. Let me do side, side, side for the sake of this check. Now, in triangle QUR, we have a side length of 9, 10, and 14. In the supposed similar triangle here of QTS, we have 15, 7 plus 14, and 4.5 plus 9. Let's ensure that we find the two corresponding, all corresponding side lengths by size. 9 is the smallest here. 13.5 is the smallest here. Let's compare those two. 9 with 13.5. Is it the same here as 10 over 15, the mids, and the same as 14 over 21. Now 10 15ths is 2/3, 14 over 21 is 2/3, 9 over 13.5. You divide them both by 4.5, you will get 2/3. That all checks out. These side length sets are all in proportion with each other. So triangle RUQ is similar to triangle STQ. Triangle RUQ is similar to triangle STQ. This is by side-side-side similarity. And once again, I could have done side angle side. What I would do is say Q is congruent to its... Listen, you have other options. No, you don't. I would say Q is congruent to itself by the reflexive property. I would only test these sides here and here. I would not test that set. And I would use side angle side off that. I didn't, but I could. All right, we have 2 more problems to do. But before so, let's look at this last example set. This is where that side splitter theorem thing... Oh, before I move on, it doesn't look like these things use side splitter. Oh, well, it kind of does on 16. But let me point this out on these problems here. Like number 14. Another valid test is 4 over 8 equals 3.5 over 7. And section 8.6, triangle proportionality theorem, does show that. You don't have to do 4 over 12 and 3.5 over 10.5. You could do just 4 over 8 and 3.5 over 7. There's a thing to that. Okay, let's go ahead and do the next set, though. Let's look at the example. Now, in this example, you have an angle bisector in a single triangle, and it does create a certain proportionality set here as well. This proportionality set shows x over 5 equals 15 over 8. X over 5 equals 15 over 8. So with that in mind, you know, that's the split. I think we did a proof. I'm not going to really get into the proof, but once you start to see more of it, it's in one triangle and the other corresponding part of the other triangle, in one triangle, corresponding part of the other triangle. They cross multiply, they solve for x, okay? And that is the length of 9.375 units. So in this problem with the angle bisector on 17, we'll make sure to have the same kind of setup. Let's look at number 16. Number 16, find the length of AB. Find the length of AB. Now AB is just this segment that's right here in green. Now this has that same split part that what I was showing here, this over this equals this over this, provided that you know that the lines are parallel. Now I know these lines are parallel because corresponding angles are congruent, and then lines are parallel by the converse and things like that. This also has congruent corresponding angles here, literally corresponding angles, not like triangles corresponding angles, but corresponding angles. That means these lines are parallel as well. And because you have parallel lines here, that means that you can do and I'm going to call this x here. You can do an x over, say, 7, the one below it, x over 7, boom over boom equals boom over boom 6 over 4. And I know I'm not getting deep into the whole, like, this is why it's allowed, but this is when it's allowed. So equals 6 over 4. Look, I'm just going to cross multiply and solve. I get 4. Actually, I'm going to multiply both sides by 7. Multiply both sides by 7, and you get x equals 42 over 4, which honestly I should have reduced 6/4 first, because now I don't know what this is, which is 21 over 2, or 10.5 units. This or that works. That's number 16. And last one, number 17, you do have that triangle breakup from an angle bisector. And from an angle bisector, they want to find the length of AB. Once again, I'm going to call it x. So finding that length of AB stems from doing that proportionality set. I can do something like 18 over x equals 10 over 4. And I say I can do like that because there are like 16 different ways that you can make this written. So 18 over x equals 10 over 4. There are ways to do it incorrectly. It's by doing parts that don't correspond, by doing them in a separate direction, things like that. Those are the things you really want to avoid doing. This one has the correct direction. Didn't matter where we started, but correct direction, and go into corresponding parts. I'm going to reduce 10/4 before I get multiplying across where I get 5/2. Let's cross multiply and get this, and divide both sides by 5, and you get 36 over 5, which is 7.2. And there's the length of x. And guys, that ought to do it for this one here. Got under the hour. This is Mr. Robinson. Thank you so much for watching. This is the Chapter 8 review. Again, there are other reviews to come. And if you need to check out some of the other problem sets with other sections from 8.1 to 8.6, I have plenty number of videos for you. And you can ask questions in the comment section down below. Hopefully I can address your questions there. So thank you so much for watching. Take care, and I will see you in the next one.